In power analysis, we set the sample size based on an alpha and beta that can be tolerated. We can reverse this approach to set the alpha and beta desired and then calculate the sample size necessary to obtain the desired decision confidence. The formula shown here is useful when we are given a confidence level, standard deviation, and a margin of error. Note that a variant of this formula can be applied to a proportional situation where standard deviation squared is the product of the sample proportion and 1 minus the sample proportion. As an example, suppose we wish to determine the minimum number of samples needed at 99% confidence to assess the performance of a process with a margin of error within plus or minus 1.3 and a standard deviation of 15. At 99% confidence, this gives us an alpha of 0.01 and a corresponding critical of 2.575. Note that the sample size calculation is based off the confidence interval, and every confidence interval is a two-tail scenario. Therefore, we must divide 0.01 equally into each tail. The area in each tail will be 0.005. We use 0.005 to get 2.575 as our critical. E is 1.3. Plugging into the formula gives us a minimum sample of 883. When attempting to characterize a data set, we have two types of estimators. Point estimators are single estimated values, like an average or a proportion. Point estimation is not very useful as a means for describing a data set. Our likelihood that our point estimate will not agree with the true population parameter is very high. Interval estimators takes a point estimate and creates a plus or minus interval around the point estimate based on a level of confidence, standard deviation, and sample size. Recall that confidence intervals are two-tail scenarios. Also, the central limit theorem will play a role in the final form of the confidence interval, hence the square root of the sample size in the denominator. We have three unbiased estimators that are ideal for describing and predicting the behavior of a population. They are mean, proportion, and variance. We have two formulas for the confidence interval of a mean. Our decision process for selecting the correct formula comes down to a handful of criteria. First, recognize that a bell-shaped behavior must be evident regardless. If we know the population standard deviation, then we lean toward the top equation, regardless of sample size. Note that this equation uses the normal distribution. If we do not know the population standard deviation and the sample size is very large, it can be argued, based on the central limit theorem, that either formula will work. Recall that both Z and the student's T are bell-shaped, and that as the sample size increases, the student's T becomes the normal distribution. Conservatively speaking, the bottom equation is probably the better choice, especially if the sample size is small. As discussed earlier, student's T is based on an alpha and degrees of freedom. Degrees of freedom is the sample size minus 1. The confidence intervals for the mean are centered at the sample mean. This is not true for variance. Here, the chi-squared distribution is used. This distribution is not necessarily symmetrical. Note that S squared is the point estimate of the variance. N is the sample size, and the chi-square statistic is based on alpha and the degrees of freedom, N minus 1. For large sample sizes with NP and N times 1 minus P, greater than or equal to 5, the normal distribution can be used to calculate a confidence interval for a proportion. The formula is given here. P hat is the point estimate for the proportion. N is the sample size, and Z is the critical statistic based on a given alpha.